All right. Waiting for this to save, and then we'll get a new page. Okay, here we go. So, integration by parts. Here we go. We're going to start off with integration by parts. I'm going to go ahead and do this first one here. All right, so integration by parts. Remember that the formula here that we have is I'll write the definite integral version here. And so the integral of u dv is equal to uv on the boundary minus the integral of v du. So I'll encourage you to watch my integration by parts videos on that. The principle, the heuristic to remember is Lyautze. So for this first integral, I'll select u equals x cubed, dv equals e to the 2x dx, so the rest. And then as I said, follow your path, right? Let's see if this works out. There we go. So du is 3x squared dx. V is 1/2 e to the 2x, just integrating that thing. And we follow our path. So uv okay, then minus the integral of v du. So 3 over 2 x squared e to the 2x dx. Okay, and some of you that are really familiar with this are probably screaming at the screen right now, just do the table, just do tic-tac-toe, DI or whatever. It's like, I know, but I'm just demonstrating like how to do this so-called classical way. Okay. We've got to be careful here. Hot tea. Alright, and then for this one we'll have, I'll just ignore the 3/2, so u equals x squared, dv is e to the 2x dx. Okay. And if you're just coming into the chat, just say hello. Alright, so the first thing here is going to be the same. And then I'll pull 3 over 2 out. Then I'll have uv 1/2 x squared e to the 2x minus the integral of v du. Notice that 2 times 1/2 is 1. Okay, so we'll have x e to the 2x dx. Okay, and let's get ourselves some more Tchaikovsky on here. Please, already have Stravinsky, Red Spring, One Lake, 1812 Overture. Yeah, let's do 1812 Overture. Okay. And then for this last one, we'll make similar choices here. You notice there's a pattern here, but this is basically the gist of integration by parts here if you do it the classical way. Okay. So and I have some stuff here. Right, so 1/2 x cubed e to the 2x minus, let's go ahead and distribute all this through so I don't have to worry about it later. And then for that last integral, okay, so for this one here, okay, we'll do parts on that one. So just by using the formulation there, so uv minus the integral of v du. Okay, note that the integration by parts formula has a minus sign built into it, okay? E to the 2x over 2, nope, same thing. That's exactly the same thing. So in fact, if I do it like this, exactly the same thing, except the 1/2 in front just makes me know that I'm multiplying by 1/2, so it just makes it a little cleaner here. It's the exact same thing. E to 2x dx. And that last one is actually super easy. So, you go through all the work here, simplify. Let's see, 3 over 4 x e to the 2x, and then that last integral, okay, integrating e to the 2x, that's again, well, we've done that enough. Just divide by 2, keep the same thing. So 3 over 4, and then another 1/2 comes in there, so 3 over 8 e to the 2x, plus a constant, and that's it. Okay, so that's doing it the long classical way. Okay. So this is how you do it classically. If you have to do like parts once or twice, so this isn't too bad. This table method, okay, is done by when you have an integral of a polynomial against an exponential sign or cosine. So the other way you can do this here is, so let's write down this integral again. We'll set up 2 columns, a D column and an I column. D corresponds to your U choices. And then I is your dv. Okay? One side you differentiate, the other side you integrate. So we're going to put x cubed in our D column, e to the 2x in our I column. Okay? And we're going to differentiate on the D column until it vanishes. So we'll get 3x squared, 6x, 6, 0. And then I'm going to integrate as many times as I differentiated in the I column. So each of these is just going to be dividing by 2. So 1/2 e to the 2x. Okay. And listening to this makes me want to play the Hasbro PC version of Risk. Think about that horn line. All right. Now in the margin, alternate signs, plus, minus, plus, minus, plus. And then we're going to connect the first thing in the D column to the second thing in the I column. And likewise, tic-tac-toe. Okay, so we're just going to multiply through, keep the signs. All right, and then simplify as needed. So what do you get? X cubed e to the 2x over 2. That's the first term. Plus highlight so you can see it. X cubed e to the 2x. Check. 3x squared times 1/4 e to the 2x with a minus. Check. Okay, 6x times 1/8 e to the 2x. 6 over 8 is 3 over 4, so check with a plus sign. And then 6 over 16, that's 3 over 8 with a minus. Check. Same exact thing. All right, so use the table if you have a polynomial against exponential sine or cosine. All right, let's show one where you have to be a little careful with your signage here. And this one we'll just do with the table method just to speed it up. Y cubed cosine y dy. Okay. This one's still set up for the table method because we have a polynomial against cosine. So we'll set this up again. D, I. I want to differentiate the polynomial. I want to integrate the cosine. And now this is again where you have to be very careful with your pluses and minuses, okay? So differentiate, and then integrate cosine until we have the same number of lines. So integral of cosine gives me sine. Again, gives me a negative cosine. Then negative sine. And then a plus cosine. I don't know why I have to like stop and pause at that. Okay. Plus minus, so get your signs in there. Build your shoelaces. Tick, tack, toe. And now you just read it off. Okay, so we'll do, this gets, let's see. First shoelace is y cubed sine y, with a plus sign in front. Then I have minus 3y squared times negative cosine y. I have two minuses there. Minus times minus is plus. So that's a plus 3y squared cosine y. So again, be careful there. Plus 6, a positive 6y times a negative sine y. So that's a net minus. And then minus 6 cosine of y plus a constant. That's it. Table method kills this problem pretty easily. Okay, so again, just be very careful with those plus and minus signs. Okay, it's very important that you do, especially when you're integrating with sines and cosines. David, yes, I'll definitely show some where you have to do some clever manipulations outside of the table. In fact, I actually want to do this next one here. I cannot put that there. Also, my favorite coffee mug here, Rocco's Modern Life. Some of y'all are probably too young for that show. 1993 to 1996. Okay. Let's do this one here. I like this next one here. An exercise in your homework set was probably integrating just arctan x, but now we want to integrate x squared arctan x dx here, okay? This is one where the table method doesn't really get you anywhere, but you can actually kind of start to set it up. If you watch a black pen, red pen, which by the way, you know what? Let me go ahead and God, I wonder if I can real quickly I love this one here. So black pen, red pen. Yeah, so there's also this like black pen, red pen does demonstrate the DI method here. I'll just throw this in the chat for y'all. Excuse me. Okay, I'm really feeling the throttle here. Yeah, so there you go. That video, black pen, red pen demonstrates the DI method and just how it organizes your information. I'm more of the fan of, if you have to use integration by parts without the table, just write U and dv for the classical method, because that encourages you to like remember what the formula is. But there are many ways you can organize your information. So here, the I in Lyautey stands for inverse function, and I have an inverse function here, the inverse tangent function, arctan. So I'm going to go ahead and set u to be arctan, because that's an easy derivative to do. And dv is x squared dx. Okay. And now I just do the rest here. So du, the derivative of arctan is 1 over 1 plus x squared. Okay, and then v is 1/3 x cubed. Ooh, that's going to be a little annoying here. Shoot. But that's fine, we can do it. So now we follow our path, right? U, v minus the integral of v du. So now we'll do, let's see, 1/3 x cubed arctan x. Oh, actually, I just realized there's a substitution that makes this work out nicer, I think. Oh, yeah, I probably could have done that. Okay, it's fine. Many ways to attack an integral, don't worry. Oh, wow, 6 frames? That's not good. Okay. Minus the integral of v x cubed times x cubed over 1 plus x squared. Okay. We're trying. Right, and it looks like yep. Oh, mute's gone because I'm running out of memory. Oh, this is fine. This is fine. Let's get a break a little. So, this may be looking ahead into the integrate rational functions. But okay, if you do the polynomial long division here, it doesn't really end up being that bad. I think I probably could have made this easier by setting x equal to tangent y at the beginning, but yeah, you live and learn, right? Okay. So let's do the long division here off to the side real quick. X cubed divided by x squared plus 1. Okay, so I can do an x here. Okay, so then we get x cubed plus x. Okay, and I get a minus x out of there. All right, so that last integral, we get 1/3 x cubed arctan x minus 1/3 times the integral of x minus x over 1 plus x squared. Now, the second term in that last integral, okay, that second term in that last integral, that can be achieved by a u substitution. So I'll go ahead and actually spell that out here in the next step here. But notice that the first term is really easy, right? First term is really easy. Integrating x, that's just x squared over 2, so I get a x squared over 6, okay? Sure, 1 over 6 x squared, same thing. Okay, verify to yourself that that does work. And then I'll have, well, minus times minus is a plus, so I'll have 1/3 of this integral here. Okay, and now what the substitution to be made here, I'll set y equal to 1 plus x squared. So dy is 2x dx, okay? And now if I play for the match, I get 1/2 dy equals x dx, and now you see that this is just going to be a natural log integral. So let's see what comes out of here. Okay, so I'll have x dx, that's 1/2 dy, and 1 plus x squared, that's just going to be y. So that just is a natural log integral. So I'm going to skip a few steps here just so we can get to the end here. We get 1/3 x cubed arctan x minus 1/6 x squared plus 1 over 6 natural log of absolute value 1 plus x squared plus a constant, and that's how you do parts. Okay, that's just how you do parts. Okay, hopefully I didn't lose some of y'all from network issues or whatever. But if you're still here, thank you for sticking around. Okay, lots of math to be done here, lots of integrals, lots of calculus. All right. Um, Let's see if I can get some music back on here without throttling the memory. So that was a very good application of integration by parts right there. I want to do one more with the logarithm. Okay, and then yeah, let's do. Where is it? Let's do that. No, I like that one. Okay. All right. In the meantime, um, let's see. All right, let's get some Stravinsky here. Let's do another integral. I like this one. I like the look of this one here. And remember, for integration by parts, if there's a definite integral and you have to change variables, remember, you just do the same usual thing that you would, right? Change the limits of integration as well. I think this will be my last integration by parts problem here. There's a couple of ways I can attack this. I can make a priming substitution by getting rid of the log x there and use like push forwards. But I'm going to show how to do this just directly by straight up using integration by parts here. I think this was a homework exercise you were assigned as well. So let's see. I think the trick here is to set. Yeah. Okay. Here we go. U is equal to the square of log x, and dv is equal to dx. All right. Different color here. Du is 2 log x over x dx. Okay. Just power rule plus chain rule there. Okay. And then v is x. Follow your path. So let's write down everything here. U times v, so x times log of x squared minus the integral of v to u. So let's write down everything here. 2 log x over x times x dx. And notices that I have that the x's will vanish. And so now just reduce to integrating log x here. And this one is actually an easy integral. This is another classical way of doing integration by parts, where again you have that invisible 1 sitting there. Because remember that dx is 1 times dx, okay? So we're going to actually do that same kind of thing here. So u equals log x. dv equals dx. Du is equal to 1 over x dx. And v is equal to x. Right? So that x log x squared comes along for the ride. Minus, and now we do this because we have a minus sign and I'm subtracting away a big integral thing. uv, so x log x, minus the integral of v to u. Well, x times 1 over x is just 1. And now you just see it, right? You can also do this with a priming substitution. Then we have plus x here. That's it. Okay. This one, the way I would naturally do this is by setting x equals e to the y, and everything just collapses nicely. Right, once again, folks, thank you for sticking around. Right. Yeah, so this one you can do a priming substitution. There's like a whole slew of ways that I could do integration by parts and show it off, but I wanted to get to some of the trig integrals because those are going to really take some time. And I'm just going to go ahead and jump to trig substitutions because that jumps ahead to us for us to actually do the class of trigonometric integrals as well. All right. All right, so let's go ahead and do some trig integrals here. Now I want to do this first one here. So we have x squared over square root of 1 minus x squared. So a lot of the substitutions for the trig substitutions are motivated by those Pythagorean identities that we should remember from pre-calculus. I won't go into them here, but I encourage you to watch that video. Okay. So I see a difference of squares in the square root in the denominator, and the square root doesn't necessarily matter. I'm just looking for sums and differences of squares. So what I need, okay, is sorry, just swapping a few things here. So what I'm going to do is this is going to be motivated by 1 minus sine squared equals cosine squared. So let's put that as a hint here. 1 minus sine squared y equals cosine square of y. Okay, and you see that kind of looks similar to my integrand. Right? I have 1 minus a variable squared, 1 minus a variable thing squared here. So I'm going to go ahead and set x equal to the sine of y. Okay. Set x equal to the sine of y. So we have, let's see here. Dx is equal to cosine of y dy. And this is where we got to be really careful about just the operations that we're doing. Okay, so this integral becomes, let's take a look here. X squared, so that's the sine of y squared times cosine of y dy for dx. I hear one of my dogs here, I think. Okay. And then in the denominator, we have square root of 1 minus sine square y. Okay, now don't be thrown off if you want to use theta for the new variable. That's fine. I'm just using y because my thetas will get very sloppy once I have to write them over and over again. So let's do some cleanup here. On the bottom, 1 minus sine square is cosine square, the square root of which, okay, is, well, if we ignore absolute values, just cosine of y. So I got a cosine of y down there. On top, sine square y, cosine of y. And now you see that my cosine of y's will vanish. And I'm now just left integrating sine square y. Okay, so now whenever you have even powers of sines and cosines, and those are the only things that are left, you're going to have to use that power reduction formula, the half angle formula. And let's remind ourselves of what that is. So, sine square y is equal to 1/2 of 1, is it 1 plus or 1 minus? Let's see here. I think it's 1 minus. I'm not entirely sure. I'm sure it's 1 minus. Heck did I? Oh, there it is. I think it's 1 minus. See, this is just what you have to do when you study, right? If you don't remember something, just look it back up. Okay, so it's 1 minus cosine 2y. 1 minus cosine of 2y. Okay. So I'm just going to go ahead and make that replacement. Shit. Okay. I personally find it's a little easier to work with the half angle formula in this form. Okay. So that is just easy. So we have y minus, let's see, 1/2 of sine of 2y, just some trick stuff and backhanded u substitution. Okay, but remember that my original problem is an x, so I need to use my original substitution, okay, to get me where I need to be. So for this step, we need to draw our reference triangle. Okay, so we have x equals sine of y. Y is our angle. Okay, sine of y, that's opposite over hypotenuse. I can get the missing side by Pythagoras. Okay, so y here, y is just arc sine x by using inverses. And then sine of 2y, I have to use the double angle formula here for the sine. So sine of 2y is equal to 2 sine y times cosine y. And I can see here, cosine y, cosine is opposite, adjacent over hypotenuse. Square root 1 minus x squared over 1. So now when I plug everything back in, okay, 1/2 y is arc sine x, so 1/2 arc sine x minus 1/4 of sine 2y, so 2 sine of y is x, cosine of y is square root 1 minus x squared. Okay, and now once I clean up here, I get 1/2 arc sine x minus 1/2 x square root 1 minus x squared plus the constants, and we're done. Okay, so we've tackled how to do a trig sub here and how to tackle a basic trigonometric integral. Now let's do another one that might give us something a little more fun here. 142 looks good here. Square root x squared minus 25 over x dx. Need some water here. So this one's different, okay? So the other one, we had number squared minus variable squared. Now I have it the other way around. So this is motivated by secant squared y minus 1 equals tangent squared y. But notice that I have some numbers out there, so I have to account for those squares. So what I'm going to do is, and again, notice that this is supposed to be the same as this. So I'm going to set x equal to 5 times secant y. So dx is 5 secant y tangent y dy. Okay. So now we got to do the laborious task of cleaning everything up here. So this integral, let's see, inside the square root we get 5 secant y squared minus 25. Dx is, oh boy, 5 secant y tangent y dy divided by x, which is 5 secant y. Thankfully, I see some stuff that vanishes here. So the 5 secant y's will drop. On the inside of the square root, I have square root of 25 secant squared y minus 25 times tangent of y dy. And if I factor out 25 out of the square root, let's actually do that here. So notice I have 25 times 1 minus secant squared, secant squared y minus 1. And so that's 25 tangent squared y. And when I take square roots, I get 5 tangent y. So bypassing all that, we get 5 tangent squared y dy. All right. All right, so now the trick here is when you integrate just with tangents, you want secants. So I'm going to write tangent square. I'm just going to rewrite it again as above because I know how to integrate secant squared. All right, and then you should see everything fall into place here. Integral of secant squared is tangent minus the integral of 5, which is 5y. And you may, you're gonna have to like do the reference triangle. Easier to do by parts. Admittedly, I haven't actually done this one by parts. But at least at the university whose review I'm doing this for, we're taught to do this just by the trig substitutions, just recognizing sums and differences of squares. I encourage you to do it by parts if you can figure it out. Actually, maybe with parts, it's yeah, parts might be a little messy in my opinion. So let's do some reference triangle stuff here. So remember we have x equals 5 secant of y. So x over 5 is secant of y. All right. And so this already tells you that y is equal to arcsecant of x over 5. But then this, you got to draw your triangle. So y is the angle. I like to think about this in terms of cosine. So turn that down a little. So let's see, if we do secant is the reciprocal of cosine. Let's write that here. 5 over x equals cosine of y. And now I have everything. Cosine is adjacent over hypotenuse. Missing side by Pythagoras. Okay, so the tangent of y is, let's see here, square root x squared minus 25 over x. And now I just keep replace, and I'm done. Let's see here. 5 arcsecant x over 5 plus a constant. Probably many different ways to write this, but this one works out. Let's do 143. I think that one's going to be a good one to do next here. Just to demonstrate some of the other techniques here. Okay. So, 143 we have, I'm just going to change the variable here. X cubed over, what is it? Square root 9 minus x squared dx here. All right. I see a difference of squares. This is motivated by 1 minus sine square y equals cosine square y. But then I see the 9, so I think square root of 9 is 3. So we have, I'm going to go ahead and set x equal to 3 sine y. Dx is equal to 3 cosine of y dy. So now we're just going to go ahead and replace. So let's see here. X cubed, we get, well, let's just write it in. 3 sine of y cubed. Dx is 3 cosine y dy. Then inside the square root, I have this. All right, now we got to do some manipulations here. I'll spare you the details here. 27 sine cubed y there times 3 cosine of y. The square root reduces to just, so on the inside the square root, we get 9 sine y. 9 minus 9 sine square y gives me, and the square root will give me a 3 cosine of y after you use some manipulations here. And thankfully some stuff vanishes, and now I can demonstrate another technique here. So we have 27 sine cubed y dy. Oh boy. So the trick for this one is I want to peel away one sine. So I'll show this one here. I'll pull the 27 out first. I'll peel away one of the sines. And the remaining sine square y, I'm going to write as 1 minus cosine square y. All right. So when I multiply that out, the first integral is easy. So let's kind of multiply those two out. Sine of y minus sine of y cosine square of y dy. Okay, and now the second integral, the sine of y cosine square of y, that's a substitution that's involved there. So just for the second integral, I'm going to do u equals sine of y, sorry, cosine of y. And so du is minus sine of y dy. Some stuff gets shuffled around, you'll see. So 27 times minus cosine of y minus the integral of minus, okay, u squared du. Okay, you can see where that comes from. We're collecting everything over. Then a 9 cosine cubed here. So the steps there, push the minus through, so you get a plus u squared there. Integrate that, u cubed over 3. U was cosine. So then you get a 1/3 cosine cubed y times 27, that's 9. And so now I just need the cosine. And thankfully I just used my reference triangle again. So with x equals 3 sine of y. Oh yes, this part. One of my field shows in high school is based off the finale from Firebird. In this nice 7/4 bit. Get the trig ratio by itself. Pythagoras. And you see cosine of y. So now you do the manipulations. I remember that 3 cubed is 27. And I'm just going to be lazy and leave it like that. Yes. You're right. Let's see. I do want to do one more with secants and tangents. One that looks really manageable. Yeah, let's do 152. This will be my last trig integral. I don't want to go to partial fractions. Let's set this one up and then we'll choose a new track here. All right, let's see here. Let's see. What do we want to listen to? Okay. I got a nice another one here. Okay. So this one I see sums of squares. So I'm actually gonna use a tangent sub here. This one's motivated by 1 plus tangent squared equals secant squared. So I'll set Elden Ring. Well, which Elden Ring track? Oh no, I wish that reminds me Spyro. Oh, Spyro would be such the Spyro soundtrack would be a good uh chill bit to do. All right. So I'm gonna set x equals tangent y here, and dx is secant square y dy. Okay. Um. So now we're gonna go ahead and manipulate tangent of y squared, secant square y. Great Fairy's Fountain. Is that from a game or? I mean, mind you, I haven't really kept up with like a lot of the big uh action adventure games. Like I haven't really played Elden Ring, haven't played Dark Souls. I've been playing a lot of Yakuza though, like a dragon. 1 plus uh although the N64 Zelda games have great soundtracks, I know that. So let's go ahead and manipulate this tangent square y, secant square y, and then on the bottom, okay, 1 plus tangent squared is secant squared, the square root of which is just a singular secant. So now we have this tangent square y, secant y, dy. And for this one, um, okay. I can write tangent as secant square minus 1. I have to integrate secant cubed. Oh, I know the trick here. I got it. Okay. I know the trick here. We're going to write everything in terms of sines and cosines. Change this sine over cosine. And secant is 1 over cosine. Oh, this is dirty. This is so dirty. So, yeah, I figured it was Legend of Zelda. I just couldn't remember which one. Let's see here. Actually, let's see if I can get some more people on the stream here. Yeah, I think if you write this in terms of sines and cosines, it should work out to be a little easier. 3 cosine square. No, I don't think so. Let's see here. I'm gonna write sine square as 1 minus cosine square. I'm gonna see if that helps out any. No, that doesn't help out any. Oh, how do I do this one? I remember doing this one a long time ago. Oh, I'm a dingus. I'm such a dingus here. Set v equal to cosine y, and dv is sine of y minus dy. I think. No, Ocarina of Time. Okay, yeah. I started Ocarina of Time. I just never finished it. I just can't really invest the time to really do that. That's that's also not the right substitution. All right, I'm gonna have to cop out here. I need a hint here. I know I've done this integral before. Let's see here. Okay, yeah, there is some dirty stuff going on here. Yep. Yep, I'm right. There's a dirty integration by parts here. I don't want to do that. It's not something that you'll normally be tested on, so, Oh, so that happened. Okay. Alright. Um, I'm not gonna finish this one, unfortunately, but you can kind of see how to set this one up. I'm gonna go and do, let's see here. I want to move on to partial fractions. A lot of these will just be like, do the algebra. Yeah, there's a dirty integration by parts here because this reduces to secant cubed y minus secant y. And secant is okay enough to integrate on its own, but secant cubed requires a lot of dirty manipulation. So I really don't want to go through that one. It's gonna be annoying if I actually show that. All right. In the meantime, well, let's go ahead and let's pick set up a problem first. We'll get our new track here. All right, 197. Here we go. We'll start with that one. And let's go ahead and listen to number 4. Then listen to some more Tchaikovsky. All right, let's look at this integral. So this is a rational function, and the way that we integrate these are with the partial fractions. Okay, so the idea is to first write this. Ooh. There we go. Partial fractions. So we're going to note that the denominator can be factored as, let's see, x plus 4, x minus 2. So the goal is to write this as, since I have distinct linear factors, a number over x plus 4 plus a number over x minus 2. And from there, the integral is easy. So there's lots of ways you can do this. I actually learned a way to do this in complex analysis, something residues, a nice clever way of cover up. But you clear the fractions here, and when you do that, you get 3x equals a times x minus 2 plus b times x plus 4. Okay. And now you just choose some clever values of x, or you can, set up a system of linear equations if you like, linear algebra. I like the cover up method for this one. It takes care of things pretty easily. So if x is equal to 2, then notice that the a term vanishes. On the left, I get 6 equals 6b on the right. So b is equal to 1. And if x is equal to negative 4, okay, again, just choosing clever values so stuff vanishes. Okay, let's see, negative 12 on the right. And on the left, the b term vanishes. Negative 4 minus 2 is negative 6. That's an A. A is 2. So now I have my decomposition. And what happens now is my integral I just use the formula that I set up here, the recipe. Watch that video. 2 over x plus 4 plus 1 over x minus 2. This is just a linear combination of integrals that come out to be logs. And don't forget the absolute values, kids. I'm going to leave it like this. I don't have to combine the logarithms. Okay, but the only hard part in partial fractions is just doing the algebra, okay? Getting the decomposition done. Okay. All right, let's do a few more. Do they have ones with repeated? No. That's funny. I'll only show the simple cases. Repeated. Just remember that you have to count up. Well, let's do 203. Or actually, 198. 198 sounds good. That's a little more manageable. Okay, so oops. Let's see, for this one, the denominator factors as x times x plus 1 times x minus 1. Okay, because x cubed minus x, same as x times x squared minus 1. So you have x, x minus 1, x plus 1. Okay. And then now you just set up the partial fractions recipe. A over x plus b over x plus 1 plus c over x minus 1. Okay. Set up for the cover up here in the way that I like doing it here. So multiply fractions, so clear the fractions, okay? Be very careful about it, by the way. b times x minus 1 plus c times x plus 1. Now choose your convenient x values. So if x is 0, I could just do this by residues. Actually, I think this one was on my complex analysis final. Something similar to it was actually. So x equals 0. The b and c terms vanish. You get -1 on the right, so a is equal to -1. If x is equal to 1, okay, we have, let's see here. The a and b terms vanish. So we have 2c. So that means c is equal to 1/2. And if x is equal to -1, I should get something similar here that I think b is -1/2. Oh no, I'm sorry, that should be b. B is equal to, yeah, 1/2. And if x is equal to -1, a and c vanishes. Wait a minute. Hold on. If x is equal to 1, a and b vanish, so c is left over, yeah. So if x is equal to -1, a and c vanish. -2 times -1 is a +2, so I get a 1/2 out of that for b. Okay, just kind of going through these kind of fast. Okay. Now we're set up for our partial fractions integral. So this is now a linear combination again of 3 log integrals. Well, a is -1 here. Okay. And it's just straightforward. Minus log absolute x plus half log x plus 1 plus half of log x minus 1 plus a constant, and we're done. Okay. All right. I want to do one with an irreducible quadratic. Oh, there was one there. Okay. So let's do this one with a quadratic here. Yeah, 207. So the quadratic here has complex roots, and so we call it irreducible over the real. So I'm just going to leave it as a real thing. You could do partial fractions with complex numbers, but, at this stage, don't worry about it. So I'm already going to tell you it doesn't factor. You can complete the square and do some cockamamie substitution if you wanted to. This completes the square as x plus 1 square plus 5. Yeah. And you get complex roots out of that. I think you get... No, you don't get something like golden ratio-esque. You could try, but yeah. Okay, so... the way this works now, I need to break this up. X squared plus 2x plus 6. Oh, okay. A number over x minus 4 plus bx plus c. So when you have an irreducible quadratic, at worst, the numerator is linear. Now, this is where you kind of have to do some extra work, or if you want to just pass through a system of equations. So 2 equals a times x squared plus 2x plus 6. So that's kind of going to be annoying to do. Plus bx plus c times x minus 4. So the one clever value that I can choose for x is x equals -4. It makes my life a little easier. So x equals -4 gives me 2 equals... Well, the b and c terms vanish because 4 minus... Oh, sorry, that should be a positive 4. 4 minus 4 is 0. So the b and c terms vanish. For the a term, we get 4 times 4, 16 plus 8. 16 plus 8 is 24, plus 6 is 30. So a is equal to 1 over 15. And as another clever choice, I'll set x equals 0 so that the b term vanishes and I now have c left over. And now I'm just going to use the fact that I know what a is. So we have 2 over 15 times 6 plus, let's see here. 0 minus 4 is -4. So we get a -4c here. So 2 is 30 over 15. All right, now I divide by -4. So let's see. 9 over 2, so 9 over 30. So let's just simplify this. Divide by 3, 6 over 5. So, let's see, 18 divided by 4 times 15. Yeah, 3 over 10. So if everything works out, I have this right. Okay. Now to get b, I'm gonna go ahead and set x equals... I'm kind of running out of clever options here, so I'll set x equals 1 here. So I'll set x equals 1. So on the left, we still have 2. On the right, 6 plus 2 is 8, plus 1 is 9, so 9 over 15 plus b minus 3 over 10 times -1 minus 1 minus 4 is -3. And this is the annoying part of this is just the algebra. 30 over 15 minus 9, that's 21 over 15. Minus 3b plus 9 over 10. I do well to simplify this a little. So divide through by 3 on the left there. That's 7 over 5. So now I have 14 over 10 minus 9 over 10. That's 5 over 10. So that's 1/2 equals -3b. So b is equal to -1 over 6. Oh, God, I hope that's right. That's why I have a CAS. Where is it? There we go. So let's check this real quick on the CAS number. Okay, it looks like I botched the decomposition somewhere. A is 1 over 15. Um, just note that when I plug in x equals 1, I get 9 in that coefficient, 9 times A. So that's 9 times 1 over 15. And it says that like my decomposition is incorrect here, just by checking my cast here. Oh no, wait a minute. No. That's right. A is right. B is incorrect for me, and so is C. Um, yeah, my B and C are incorrect here. Yeah, this is like where sometimes setting up a system of equations might be a little friendlier to solve. Like this one, you gotta do a lot more careful work here. Let me demonstrate how to do this with systems of equations. And yes, I'm keeping all this in the VOD, so sorry. Actually, let's look at that. 2 over 15 times 6. Okay, so again, that's when we set x equals to 0, right? So if I set x equals to 0 in the quadratic term there, okay, 0 squared plus 2 times 0 times plus 6. And you got me. You got me. Yes, you got me. There you go. Excellent work. Sharp eye. No, I got sound alerts. Okay, I got sound alerts. So this is where I would normally hit the mystery biscuits button. So I got sound alerts. So 30 minus 624. So minus 6 over 15, which is divided by 3, minus 2 over 5. There we go. Okay, now I'm getting the decomposition now. Yes, thank you very much. Thank you very much, mystery person. Yeah, if only I could thank you properly if I knew who you are if you were one of my students. All right, so now let's go ahead and tidy this back up here. I'm keeping this in, don't worry. I want to do a couple of improper integrals here. All right, so when x equals 1, we have 2 equals 6, 8, 9. 9 times 1 over 15. Plus, okay, b minus 2 over 5. I am so sorry. 1 minus 4 is a minus 3 there. Okay, 30 minus 9, 21. Okay, 6 over 5 is 18 over 5. So I subtract, I get 3 over 15 equals minus 3b. So b is equal to minus 1 over 15. Okay, God, after all that mess. Okay. Let's write down what the integral is. So a was 1 over 15. That's easy to do. B is, let's see, minus 1 over 15x plus, well, minus 2 over 5. Let's see here. X squared plus 2x plus 6. A couple of ways to do that last integral. I'm gonna go ahead and Oh yeah, if I can just complete the square, that would be so much easier to do. Alright, so here's what I'm gonna do in that last integral. I'll set u equals 2x squared plus, sorry, x squared plus 2x plus 6. du is 2x plus 2 dx. And I'm off by some scale factors here, so... There's some completing the squares here that you can do here. But let me pull out the minus, a minus 1 over... Let's see. What can I pull out here? 2 over 5 is, let's see, multiply by 3, so that's 6 over 15. We'll just pull out a minus 1 over 15 here. Hey, Jonathan, hey, nice to see you here. Yeah, there's going to be a VOD. Once the entire stream is done, I'm going to split it up into a few different parts, and I'll get it, get the VOD out as soon as possible. Thanks for coming by. Right. Oh, yep. There's there's a lot more evil here. Okay. Du over 2 was x plus 1 dx, and oh, wow, this is embarrassing. I'm just gonna cop out at this one here. You won't have something where you are required to complete the square, but I'm just gonna have to cop out here because I want to get to more stuff here. And this part of the video is actually running a little long. We're already at 7 o'clock. Holy cow! All right, let's do a couple of improper integrals just to, like, keep ourselves sane here. Now, of course, I would be pretty evil and, like, give you the improper integral I had to compute for my complex final, but damn, we're not going to do that. Also, remember, folks, I got sound alerts there, so if you are Twitch savvy and you know where the sound alerts are, go ahead and have fun with those. Let's do this easy improper integral here. Okay, integral from 1 to infinity of log x over x dx. Okay, this one's easy. I could definitely do this one. All right, so this one's an improper integral because we're integrating to infinity. So the big thing here is that you're going to want to pass this to a limit first, okay? So the idea here is this needs to be interpreted as a limit here. And now let's just use your usual integration techniques. Here's just a u substitution Although I think you can probably make this doable with parts. If I set x equals e to the y, I get y times e to the minus y. Yeah, that's possible if you do a substitution that way and do parts, but the more natural substitution here is to set u equal to log of x. And so du is 1 over x dx. And remember, when we change variables, we change limits, okay? So when x is 1, that means u is, well, log of 1, which is 0. And when x is t, u is just log of t. Okay, so just usual substitution rules. So not too bad. So this is now the limit as t approaches infinity of the integral from 0 to log t of, well, it's just u du. And this one's not too bad. Okay, we'll get 1/2 u squared out of this. Evaluate this between log of t and 0. Thankfully at 0, we just get 0. Okay. And now I got to look at this part here. At 0, I get 0. So I have 1/2 of the square of log t. But remember, log t gets large as t gets large, so this limit is infinity, so the integral diverges. So that's just pretty easy. You're just passing to a limit as the last step. That's really it. If you actually get an actual number, then that says that the integral converges. Okay. So you'll need to. This is like the intuition that you need to use for like a sequences in series. Okay. I want to do. Let's see. Oh, that one's a little evil. Yeah, let's do 360. Xbox 360. Anyone? This one is from 1 to 5. Okay. Now, notice the problem here. Whoops. No, that's right. The problem here is that if x equals 1, my denominator is 0, so I have a discontinuity. I have an asymptote there if I were to graph this. I'm not going to. So I need to pass this as a one-sided limit. This is going to be a limit as t approaches 1 minus, 1 plus, sorry. Because I'm integrating to the right of 1, which is where my discontinuity is. Actually, I better go ahead and graph this. So there's my asymptote, and my function, I guess, sort of looks like this. And I'm trying to see if this area is finite or not. Okay. So I'm only integrating to the right of 1. Ah, someone got it. Someone definitely did it. Thank you very much. Thank you very much for that. So now we have this integral here. This one can be achieved by a just a variable shifting substitution, but it's really just a power rule thing. Just to help myself out, I'm going to write it like this. Also, one of my favorites is the Mystery Biscuits sound alerts. If anybody's a Tom Scott fan here. I'm going to write this as x minus 1 to the minus 1/2. And then, okay, that's just power rule. So add 1 to the exponent, divide by the new exponent, which really here means multiply by 2. Wow. Yep, there's that one too. Of course, please use those sparingly, okay? When I plug in 5, I actually get a number here. 5 minus 1 is 4, the square root of which is 2. 2 times 2 is 4. And I just have 4 minus 2 square root 1 minus t, and thankfully that has limits. That's 4. So the integral converges and the limit is 4. Okay, so really the only extra step for improper integrals is just you're taking the limits. That's really it. The integration steps don't really change. You're just going to pass through limits. Okay. Just be very careful. Some of them you might have to do some priming substitutions, but it's just really the same type of integration that you're doing, just passing to a limit. All right. This part of the video has gone on long enough. So we'll go ahead and take another break. Grab some snacks. Drink some water. Okay. And I'm just going to go ahead and come back and talk about a series of real numbers. I won't go ahead and talk too much about sequences, okay? But I'm going to go ahead and talk about series of real numbers, so we'll come back.